Welcome to this new video. In this video, we're going to learn about the curve number. And this video actually is going to be very important because we use the curve number a lot. And by solving these problems, I'm going to also take the opportunity to explain what actually curve number is. And even though it has a few steps, uh, it's not actually complicated once you understand what you are doing. And I'm going to try really hard to make it to explain it pretty simply in simple words and what it actually is. So let's start with the first problem. 5.2. Assuming an average soil moisture condition on hydrologic soils group C, calculate the runoff volume in inches for a 100-acre suburban development with the following land use if rainfall is 4 inches. You must use the NRCS curve number method. And then we're gonna solve for this part here. It says what is the area of retention. This is not an outlet, it's a retention basin, or also called percolation basin, in square feet and acres to store the runoff rainfall excess if the maximum depth of storage is 5 feet, excluding debris storage and freeboard. Assume a rectangular pond with vertical sides. Okay, so a few things we need to notice. If you remember, we already worked with the rational method, and the rational method said we have Q equals CIA. And all this is doing is Q will be like the runoff after the precipitation. Like if we have let me do a better job. If we have a watershed, I draw something like this in previous video, and there is a slope, right? Like let's say this is the underground of the watershed. So the water is going to flow downstream, right? And we have rain falling on this watershed. So all this volume of water that is being precipitated, it's not gonna come out at the outlet because some of it is gonna be lost due to infiltration. Some of it is gonna be evaporated. Some of it is gonna be gained by the vegetation of the area, if there is any. So there is an amount of water that is gonna stay on this area of the watershed, and there is some amount of water that is gonna run off through the rivers to the outlet. So what I'm trying to say is that when we use the rational method, which is Q equals CIA, we have the intensity, which is the precipitation over a specific time period, right? So we have 6 inches of precipitation over 1 hour. That will be our precipitation, and then we multiply that by the area of the watershed, right? So this will give us the amount of water in volume that will be in the watershed. The reason we use C is because, as I explained, not all the water that falls here is gonna come out. So we need to like use, for example, 0.75, which in this case, C is like a percentage. It's saying like only 75% of all this water is going to become runoff, or runoff or Q. So this is what this runoff irrational method does for us. We need to convert how much water that is precipitating will come out at our outlet. So this rational method is not the only method. We can also use the curve number method. And the curve number follows a similar idea, except that even though this curve number could go from 0, I guess, to 100, it's not actually a percentage. And I think later in the problem I can explain why not. But if it helps you to understand it, like theoretically, you could use it like the curve number regulates how much water out of all the water that is being precipitated is actually gonna become runoff. With this said, let's start solving what this problem is asking us to do. Let me merge this. So for the runoff, we are going to need two pieces of information. One of them is the land use, which we can find on table 5.7, different types of land use. the use of the land of our watershed, and also we need the soil type, what type of soil it is. In our case, we are told that our soil type is group C, and we have these different land uses. In table 5.7, we can find different land uses and soil types A, B, C, and D. Usually, these represent different types of soil. Okay. Now, finding the values of each individual land use, we're gonna find different curve numbers for each of them in this table. Now we have the percentage of land, and this is going to help us to find the total. What would the curve number be that would represent the best our watershed that has these different types of land use? If we only had in our watershed one land use, let's say all our watershed is full of 1/4 acre residential lots, we only use, let's say if we have 1/4 for type, what type was it? Type C, we come down here to 1/4 will be 83. So our curve number will be only 83. But since we have more than one land use, we need to find a fractional curve number for each of them, and then add them up. And this number here would represent the curve number of our watershed with these different types of land use. So let's start. First, we find the individual curve numbers for 1/4 acre residential lots. So we're down here, type C. In our case, would be 83 for this. 1/8 of an acre would be, type C would be 90. So we type 90 here. Commercial area with curves, we're gonna find the name as it is here. It's not in this table, but when I solve this problem, I use this one, curves and storm sewers. So I use the value of 98 here. So we can put that in there. And open space grass cover, there is a section here, open space, and the grass is covered 85%. So is greater than 75. So you might want to use, for soil type C, you might want to use 74. And so to find the curve numbers, you need, remember these two pieces of information: what land use there are in my watershed, and the soil group of my watershed. One of the limitations of this approach is that usually in a watershed we might have more than just one soil group. So maybe this number doesn't completely represent our watershed, but this is the best we can do with this approach. Okay, now that we have each individual curve number, all we need to do to find the fractional is we need to multiply this curve number by the percentage this land use takes out of our whole watershed. In our case, it shouldn't be 40, it should be 0.4. So, what happened here? Okay, 33.2. So, and we do the same with the next ones. Times 0.2, that's 20%, equals 98 times 0.25 equals the curve number that we found times 0.15. Now the sum of all of this, it doesn't like that. This is merge. Let me. Okay, 33 equals 20 times equals 90 times 0.2 equals 98 times 0.25 equals 74 times 0.15, and hopefully this equals sum of equals sum of these values. Okay, now we got 86.8, which is about 87. Usually for this, we don't want to use decimals because all of this is an approximation. This is not like scientifically proven in a way. It's just mostly empirical. So we can just replace this value by for 87. So now we have the curve number that represents our watershed that has all these different land uses and a given soil group type C. Now that we have our curve number, we can find our storage. What storage means is, let me draw again our watershed. All it means storage in our case is all the water that is going to stay in the area, like it's gonna percolate, or so it's not gonna exit, it's not gonna run off. So we need to find what amount of all this water that is precipitating is going to stay in our watershed, stored in our watershed, and it's not gonna exit. So to find that, all we need to do is plug our curve number that we just found into that equation. 1000 over 87 minus 10. So we get about 1 point. I don't like this. I don't know why it's not working. Anyway, it's about 1.49 of storage, and let me check with my. And now that we have this value, we can use it to find finally the rainfall excess, with this equation here. And as you notice, we need the storage and a precipitation, but we were told that we had 4 inches of precipitation. So let's use that. 4 equals to 4. I'm struggling today. Equals to 4 minus 0.2 times the value of storage that we found, all of that square, divided by the precipitation, which is 4, plus 0.85 times the storage value that we found, and hopefully we get enough. It says 3, but it actually is 2.6. It just had it with no decimals. So we get rainfall 2.6. Now, this means that the amount of water that is going to run off is 2.6 out of the 4 inches of rain. And I wanted to remember, I said with the rational method we had Q equals CIA, and the C here, the runoff coefficient, works as a percentage. In our case, let's say if we have 87, for example, and if we use a similar approach, we use equals 0.87 times the 4 inches. Let's do it here. Equals 0.87 times 4 inches. It's gonna give us about 3.48 inches, which is different from 2.6. So this curve number isn't actually a percentage. It's just a number that you need to use to find the rainfall excess using this equation. So 2 things. Curve number is only a number that is gonna help us to find the rainfall excess. The rational equation method, C, it actually works. The value of C actually works as a percentage. So those are 2 differences. Now that we have the rainfall excess, 2.6 inches, now we need to find, we have found the curve number. Now they ask us what's the area of retention? What's going to be the area of the retention basin to hold all this water? So to do that, we need to find what this water is going to be in a volume, right? So what we need to do is multiply this 2.6 times the area of our watershed, which is 100 acres. So we have inches times acres. So we need to convert those acres into feet and those inches into feet. So we're gonna divide by 12 to get the feet into inches. Let me do this. Times 1/12, and then times 43,560. There are 43,560 square feet in an acre, so that will be 43,560 over 1, and that will give us let's make it about 943,538 cubic feet. Sorry, it's hard to see here. I don't know how to. Anyway, so we get this value. Let me make this a little. Okay. There we go. Okay, that's our volume in cubic feet. Now we are told that our retention basin depth is already 5 feet, and they're asking us for the area. So all we need to do now to find the area, this is the run of volume, and this will be the retention. Let's do retention basin area. It's going to be equals to the volume divided by the depth, which is 5 square feet. So that's the value in a square feet of our area, and if we want it in acres, all we need to do is convert that into acres, which is divided by 43,560, and this is our area of our retention basin in acres, 4.33 acres. So to store all that water that is going to run off from a storm like this in our watershed, given our land use, we will need at least 4.33 acres of free space to use as a retention basin with a depth of 5 feet. So these are the answers for this problem. As I said, it has a lot of steps to solve for the curve number. You need to check some tables, but the process is not that complicated. All you need to do is find the curve numbers, and if you have more than one land use, find all of them, and then multiply them by the percentage of area from the basin of each one of the land uses. Get a total curve number that will represent your watershed, and then plug in into these two equations. And that way you get your runoff value. So if you understand the concepts of it, it will be way easier for you. I hope this problem helped understand. Now let's move to problem 5.9. Okay, so in this problem we got two parts, A and B. Part A says, use the NRCS curve number method to estimate rainfall excess for an area before and after development. The rainfall is estimated at 6 inches. So they're giving us the precipitation is 6 inches. The hydrologic soil type is A. The pre-development condition, here they're giving us the land uses. The pre-development condition is open space with grass on about 50% of the area. And the post-development condition is residential with a 38% impervious cover. Part B, if the watershed were 25 acres, how many acre-feet of ponding is necessary to store all the rainfall excess from the post-development? So our how big needs to be the retention basin, right? If they're giving us the area of the watershed. So all we need to do is the same approach. Just find the curve number for pre-development and after development. And let me explain why we have two different cases. So let's say we have our area with our water, like this is the shape of our area, And again, there is like a slope, right? This is the outlet, this is the depth. When you have an undeveloped area, out of when the water is raining, sorry, when it's raining and the water is precipitating on our area, a lot of this water is going to percolate into the ground. So it's going to become groundwater because it's open, it has grass, right? But when you start developing, you start building houses, a lot of the area that the houses are taking, all the water that used to percolate in these areas, now it's not infiltrating into the ground anymore. So what's going to happen is that more water is going to run off because there is less area to infiltrate into the ground, which means that whoever lives down here is going to get more water than they used to because now this area is being developed. So what cities do, this is actually a huge problem because these houses, let's say, were not designed to receive this much water, much more water. So when a developer comes and says, I want to develop here, the city says, okay, that's fine. They run a hydrology study, and they say how much water is not going to infiltrate anymore due to your development. Therefore, you need to provide part of your development a retention basin, which will make up for all that water that is not going to infiltrate anymore. That's what this problem is telling us to do. Find the difference of water, of runoff in pre-development versus post-development. The difference tells us how much we need to develop a retention basin for. So all that water doesn't go to the houses downstream, but it goes into the retention basin in case of a storm. So this is what we're doing in this problem. That said, let's start solving for it. So we have land use. We need to find the curve number. In this case, we only have one land use on each in each case, pre-development and post-development. So we're gonna only use, let's say we have pre-development, post-development, land use, and then we need to find the curve number. So for the land use of the pre-development, we have open space with grass on about 50% of the area. If we go to our table, we got open space with grass about 50%. So it's a fair condition. And the type of soil is A, I think. Yeah, type is A. So we're gonna use value of 49. And for the post-development, we're gonna use, it says condition is residential. So we're going to use, let's see, I think I used the value of 61, and I assume the residential are 1/4 acres development. So I use the value of 61. We have now the, sorry, these values here go right here. This is the land use given us, and grass 50%, and this we're gonna use 1/4 acres. Now we need to find next the storage, the saturated storage. That's why it has the apostrophe right there. And this is going to be equal to, I have the formula here, 1,000 over the curve number that we just found, minus 10. And I don't know if this is gonna give me the same value, so I'm just gonna type it again. I guess it is. Okay, so we got 10.41, and this is 6.39. That's correct. Let's make it 10.41, 6.39, and this is in inches. Okay. Now we need to find the rainfall excess, and we again use the same formula. We have the precipitation. We were given the precipitation is 6 inches, the rainfall. So we have 6 minus 0.2 times the storage that we found square all of that divided by the precipitation 6 plus 0.85 times the saturated storage. And why it's called saturated storage? Because it's like all the water that it can hold, the watershed is gonna hold, store until it gets saturated. 1.0. Yep, that's very similar to what I got. And we do the same here. So 6, I think if I just drag it, cool. So we get about 1 inch, and in this case we get about 2 inches or 1.9 something. So I have the value of 2 inches. So this is part A. We found the rainfall for the pre-development and post, the rainfall excess for the pre-development and post-development. So we can assume that after the developers built, the runoff doubled, went from 1 inch to 2 inches. So downstream, houses were gonna get double the water they used to get. And to make up for that, we need to create build a retention basin. And this retention basin needs to hold all those 2 inches. But we know that the watershed is 25 acres. So to find the volume of the retention basin in acre feet, that's going to be equal to the 2 inches times 25 divided by 12 to get it into feet. And we get about 4.06 acre feet. So this is the volume of a retention basin needed for that development. Now let's move on to the last problem of this video. And I have some steps for this one so we can go a little faster. It says the runoff coefficient and the curve number are important parameters for the design of a stormwater holding ponds or retention basins. I like to call them retention basins. So this is what I was saying. We can use the rational method, which uses the runoff coefficient, which is like a percentage, or we can use the curve number, which is a little more specific because you develop a curve number depending on land use and soil type. And this saying is like those are important parameters or ways to design for retention basins. It says a water management district specifies the 25-year return period storm and a duration of 6 hours for all rainfall data. During this storm event, the volume of rainfall excess for a 100-acre urban watershed was measured at 725,000 cubic feet. For this area, what is the runoff coefficient and curve number? Assume that there is no initial abstraction. So for both the rational method and the curve number method, we need the precipitation. We need to find out how much water precipitated in the storm, right? So in this problem, we are not given how many inches of precipitation we got. In the previous two, we were given that. In this one, we have to find it, and that's why they give us the return period and the duration. And if you remember, to find the precipitation, we are going to use the IDF curve, and we're going to use the Orange County one. So we have a 25-year return period, which will be about the fourth line from the top for a 6-hour duration storm. So it will be somewhere, if you go to the 6 hour up to the 25-year return period, which is this one here. So you see that it's gonna be about 1 inch. And that's what I used when I solved this problem, 1 inch. So we have 1 inch, and this is the intensity, 1 inch per hour. So find the precipitation with the IDF curve. So the precipitation equals the 1 inch per hour times the duration of the storm is 6 hours. So that's gonna give us 1 times 6 is 6. The hours cancel, so we get 6 inches. And that's our precipitation. Now we need to find the runoff volume. And we need to do that using the values that we were given. So we were already told that this storm generated 725,000 cubic feet. And if we divide that by the area, it's gonna give us the runoff in inches. So let's do that. The runoff is gonna be equal to the volume 725 divided by 100 acres, and that's going to be equals to 725 divided by 100 acres, and we need to convert, that's 1,000, and we need to convert those acres into feet and then inches. So we're gonna multiply this by 12. I'm just seeing to my notes right now, so I know I don't make a mistake, and then divide all of that by 43,560, and that's gonna give us inches. You can double check this work on your own, which 1.99 is about 2 inches. So we get 6 inches of precipitation, and out of all that volume of water or precipitation, 2 inches are runoff, which means 4 inches actually stay in the watershed. They either infiltrated, they did not run off the watershed. So with that, if you remember, we have the runoff equals the runoff coefficient times the precipitation as well. We have the rational method Q equals CIA, and we also have that the runoff equals a percentage of the precipitation, and we are asked to find for the runoff coefficient. So we need to just solve for C, and we're gonna have that C equals the runoff over the precipitation. That's gonna be 2/6. So we get about 0.33, and this doesn't have it's a percentage, so it doesn't have units. This is the answer for this part. Let's change the color of that. Now we need to find the curve number, solving for the saturated storage first. And don't get confused by saturated storage. This just means like this all the amount of water that the watershed can store. So to do this, we're actually going to use this equation here. And you use this equation to find S prime only when the initial extraction is 0, because that's what we're given. And this is an equation from the book. When you just start, I think the book just starts talking about curve number, it introduces this equation. So all we need to do here is solve for S to find the storage of that. So that's gonna end up, if you play around with that equation, you're gonna end up having S equals P squared, all of that divided by the runoff minus the precipitation. So with that equation, you can find that S, let's add S is equal, the storage equals the precipitation square, which we know is 6 squared let's add another parenthesis, 6x squared divided by the runoff, which is 2 inches, all of that minus the precipitation, which is again 6, and we get about 12 inches. So the storage here says that 12 inches with a storm like a 6-inch storm, the maximum storage that this can get is 12. So to get, now we need to solve for the curve number, and to solve for the curve number we use the same equation that we have used over here, because now we have S, so we can just solve for the curve number with this equation. So if we move things around, we're gonna get that curve number equals, I have 1000 divided by S, the storage value, which is 12. Oh, I need to, equals 1000 divided by this plus 10, and it gives us about 45.4. So you can just round it to 45, and this will be the answer for this other problem. This problem is interesting because they're asking us to solve for the curve number that will represent this storm under these conditions, the volume and the area of our watershed, and you just need to use this equation right here. And I believe that's it for this video. I hope these 3 problems actually help you understand better how to use the curve number. Remember that if you have more than one land use, you can combine them into a one curve number that represents the whole watershed. And you can all, in the case like in this second problem that we solved, let's say if they gave us more than one land use, we use the same approach as the previous problem. We find the curve number of each land use and then we combine it into just one. But in this problem, we were just giving one land use per each case. So we just need to plot that because that would be the 100% of our area for this land use. And okay, I think this is it for this video. Good luck solving these problems on your own. See you on the next video.